Hey folks, I hope you're doing well. Today's short video is about inverse trig functions, which is section 6.3 in the book. So at first glance, this should seem to be a misnomer. And that is because the trig functions are, for us, sine, cosine, and tangent. We've introduced those functions in previous videos. But if you look at just, say, the sine function, so here's a graph of the sine function over here on the left in blue, or at least a piece of the sine function. And you'll notice that it's not one-to-one. It's clearly not one-to-one. It fails a horizontal line test, right? I can draw a horizontal line, say right here at y equals 0.5, definitely hits the curve in more than one place. And we know that a function only has an inverse if it's one-to-one. So what gives? Well, what we do here, and this is kind of a common trick in mathematics to generate inverses of functions that are not one-to-one, is instead of dealing with just the sine function, we restrict its domain, right? So over here on the right, what I've done is define a new function that I'll call s of x, which is really kind of a piece of the sine function. It's sine x, but we only allow x to be between minus pi over 2 and pi over 2. And so that's the graph over here on the right, the purple graph. And you can see it looks just like a segment of the sine curve. We've just kind of cut off a lot of the sine to avoid the not one-to-oneness. Well, this function with the restricted domain is one-to-one. And so we'll define the inverse sine function to be the inverse of this function, the one on the right, since the one on the left doesn't have an inverse. We'll usually write this, so this is our usual inverse notation, right? We put a superscript -1 after the function to denote the inverse, or sometimes we'll use arcsine x. So these two things mean the same. Arcsine and sine inverse are synonyms. Usually I'll use what's highlighted in blue now, but you may see this in the book and other places, just so you know it's equal to the same thing. Okay, so these two functions are inverses. Now that means that the arcsine, or the inverse sine, takes the outputs of the sine back to their inputs, right? Inverses operate in reverse directions. So whatever the inputs are for s of x, the outputs are for s inverse and vice versa. So for s of x, again, that's our restricted sine function. This is the domain because that's how we defined the domain. And you can see from the graph down here that the function goes from a low of -1 to a high of +1. So the range is the interval from -1 to 1. And that means for the arcsine or inverse sine function, those flip, right? The domain of the inverse is the range of the function, and the range of the inverse is the domain of the function. So you can see that I have just flip-flopped domain and range here. Okay, let's quickly define inverse cosine and inverse tangent. We'll look at their graphs and then do a few examples. And this will probably be a short video today, which is fine. Okay, so quickly, let's do the same thing to the cosine function. So here is a piece of the cosine function over on the left of the blue curve. Again, definitely not one-to-one. You can easily draw a horizontal line that hits it more than once. So what it will do is we'll restrict its domain to just the interval, the input interval from 0 to pi, right? So I only allow inputs between 0, which is here, and pi, of course, is a little bit more than 3. And just on this interval, the function is one-to-one, right? It's this purple curve over here. So the inverse cosine function will be the inverse of this function. And again, sometimes you'll see arc cosine instead of cosine inverse, but generally I'll use the cosine inverse notation, the one on the left. And again, as far as domains and ranges go, c of x, right, is basically a restricted version of the cosine function. We've restricted its domain to be that interval from 0 to pi. And you can see over on the right here that the range goes from y value of -1 to a y value of +1. So let's just write that down. Right, the domain of c of x is from 0 to pi, the range from -1 to 1, and that means for the inverse, those things flip-flop, right? So the domain of the inverse is going to be -1 to 1, and the range of the inverse is going to be the interval from 0 to pi. So this is important for a couple of reasons, one of which is This means we cannot take the cosine inverse of anything that's outside of that interval, -1 to 1, right? So the cosine inverse of 42 doesn't make any sense because the domain of the function is just from -1 to +1. Okay, finally, the tangent function. So over here on the left is a piece of the graph of the tangent function, right? Remember, this one has all these breaks wherever the cosine function is 0 because tangent is sine divided by cosine. It has a cosine in the denominator. You can see also, of course, that this function fails a horizontal line test pretty badly. You can draw a horizontal line and easily hit it more than one spot. So the one on the left doesn't have an inverse, but if we restrict its domain, and we'll restrict its domain to this interval from -π/2 to π/2, this is an open interval this time. At π/2, tangent's not defined because the cosine would be 0 at that point. Right, so π/2 is right about here where the cursor is, or -π/2 rather, is right about there, and plus π/2 is right about there. I'm basically taking one of these pieces between the breaks, the middle one. So I get this purple curve over here on the right. Again, this is the function I'm kind of calling t of x. It's a restricted version of the tangent function. And we will define the inverse tangent to be the inverse of this thing, right? And yet again, you'll sometimes see the notation arctan, but we'll generally use this notation, tan inverse. So what's the domain and range of t of x? Well, the domain is this interval because that's how we set it up, right? We restricted the domain to be the open interval from -π/2 to π/2. Notice the range of this purple curve, though. This curve just keeps diving down here on the left and it keeps shooting up on the right. It is not constrained to be between -1 and 1. Rather, the range is all real numbers. So let's make a note of that. Right, here's the domain. We sort of set that. And the range we can observe from the graph is all real numbers, or the interval from -∞ to +∞, if you want to write it in interval notation. And so for the inverse tangent, domain and range will flip, right? So the domain of inverse tangent will be this interval, and the range of inverse tangent will be this interval, right? So what's nice about that is that inverse tangent doesn't have any domain restrictions, right? You can take the inverse tangent of anything, any real number at all. Your output will always be between -π/2 and +π/2. Okay, so here are some graphs. I wonder if I have, oh, I guess I don't. So these pictures are okay. There are some better pictures in the book in section 6.3. So if you want to check that out, you can see better graphs there. We're not super interested in the graphs of these functions. We're more interested in sort of composing them and using them to simplify some expressions. And if we had more time in the class, we would be using them to solve trigonometric equations. Okay, a few examples. What is the sine inverse of 3? So this is a bit of a trick question. Not really, I guess, but you will recall that the domain of the inverse sine is the interval from -1 to 1, right? The same for the inverse cosine. They both have domain -1 to 1, and that means you cannot plug something into them that's not in this interval, right? 3 is outside the interval from -1 to 1, so this quantity is not defined. And if you do this on a calculator, and maybe we'll try that later on, you should get some sort of error or possibly a complex number. In any event, for our purposes, this isn't defined. There's no such thing as the sine inverse of 3 because the domain is -1 to 1 and 3 is not in the domain. Okay, let's do one. So this one is a little more reasonable, right? The cosine inverse of 1/2. Now 1/2 is between -1 and 1. So this is in the domain of the inverse cosine function. The key here is to sort of understand what this means, what the cosine inverse of 1/2 means. Well, if we let theta be the cosine inverse of 1/2, right? Well, that means the cosine inverse function maps 1/2 to theta, which means the cosine function goes in the other direction, right? The cosine would map theta to 1/2. Technically, we should be using our function c from up above, but c is the same as the cosine function as long as we stay in the right domain. So this is an important notion regarding inverse trig functions, that any expression like this involving an inverse trig function, you can understand in terms of its inverse, right? So you can kind of write the sentence either way. Theta equals cosine inverse of 1/2, or cosine theta is equal to 1/2. So really what this is asking is, can you find me an angle theta whose cosine is 1/2? And of course, we can, from our experience with sines and cosines in previous videos, we know that there are many angles whose cosine is 1/2, right? So this is just repeating what I just said. Seek an angle whose cosine is 1/2. Pi over 3 is one example, right? So cosine inverse of 1/2 is pi over 3. To elaborate a little bit here, right, if we're looking at angles that have cosine of 1/2, and you recall sort of how the unit circle setup worked, there's pi over 3 certainly has cosine of 1/2, but there are lots of angles with this circle point, right? This is a phenomenon we've encountered before. So pi over 3 is 1, 7 pi over 3 is another, right? That has the same circle point as pi over 3. For that matter, minus pi over 3 would be another. Oops, would be another, etc. So how do we pick the right one? Well, recall that the range of cosine inverse, if we scroll back up here, is this, right, from 0 to pi. So when computing a cosine inverse value, we want to make sure to pick something between 0 and pi. And looking at my solutions here, that's the only one between 0 and pi. So that's the one I want. That's the cosine inverse for 1/2. Okay, so certainly you can do this kind of calculation on a calculator and get a decimal approximation, and we'll look at some examples of that soon. But if this number is sort of carefully selected so that you can find values that have that exact cosine, you should know how to go through this line of reasoning to figure out an inverse trig value. Okay, here's another example, tan inverse of 1. Right, so using the same sort of reasoning, if we let theta be the tan inverse of 1, so that means that the inverse tangent function maps 1 to theta, well, that means the tangent function maps theta to 1, or more technically, the t function maps theta to 1, but t has the same definition as tangent as long as you're in the right domain. Okay, so I'm looking for an angle whose tangent is 1. And if your tangent is 1, it means that the sine value and the cosine value are the same, right? Because tangent is equal to sine over cosine, right? So if tan theta is equal to 1, this means that, let's see here, theta over cosine theta equals 1, and that means that sine theta equals cosine theta. Okay, so that's where I'm getting that, right? Because tangent of theta by definition is sine theta over cosine theta. All right, so I'm looking for an angle where the sine and cosine values are the same, and we know from our experience with sine and cosine that pi over 4 is the one that we want, right? So, and again, there are a lot of theta values that satisfy this equation, but we want one that could be an output of the inverse tangent function. And you'll recall that the range of the inverse tangent is this, right? Minus pi over 2 to pi over 2. So we want to pick one in that interval, and pi over 4 works as our solution here. Okay, so what about this next example, the cosine of the cosine inverse of 8 pi, 0.8 pi, pardon me. So the first thing to notice is that this is in the domain of the inverse cosine function, right? The domain of inverse cosine, let's scroll back up and make sure, is right here. Okay, so now I'm not sure if that's in the domain of the inverse cosine function. 0.8 pi, do that on my calculator. Nope, that's definitely not in the domain of the inverse cosine function. So let's change that so that this function makes sense. 8.2, that'll do. All right. Okay, so the answer to that question as it was typed would be it's not defined because you can't take the cosine inverse of 0.8 pi. It's out of range. However, we've changed the problem now. 0.2 pi is in the domain of the cosine inverse function. And here, what we're driving at is to recall that when you compose inverses, they undo one another, right? Whatever the cosine inverse maps to, cosine maps it right back where it came from. And so our solution here should be, again, not 0.5, but 0.2 pi. And again, that's just a reminder of sort of one of the basic properties of inverses. Okay, how about here is a triangle, and you can see I've marked an angle and a couple of sides, and I want to know what the angle is, right? So I want to know what theta is. Now we could easily find the other side using the Pythagorean theorem. That's not really necessary here, but you could certainly do that if you wanted to. Instead, to find theta, I'm going to use a little bit of trigonometry, and notice that just from this picture, the tangent of theta is 7 divided by 16, right? Because tangent is opposite over hypotenuse, over adjacent, pardon me, in a right triangle, right? So here is the equation that I just voiced. Tangent theta is 7 over 16. And if the tangent function maps theta to 7 over 16, then theta is equal to the tan inverse of 7 over 16, right? Tan and tan inverse go in opposite directions as long as you stay within the domain. But recall that the domain of tan inverse was all real numbers. So we actually don't have to worry about that here. And so I wind up with the tan inverse of 7 over 16. We can do this on a calculator. Okay, so let's go to Google Calculator and see how to do a tan inverse. If you, on your calculator, you may well have a tan inverse button sitting right in front of you, which is fine. You can go ahead and use that. On Google Calculator, you don't see tan inverse when you first look at the calculator, but there is an inverse button over here, this INV, and if I push that, you can see that all the trig functions become inverse trig functions, right? If I push it again, I go back to the trig, inverse trig, trig, and so forth. All right, so I want to take the tan inverse, so I'll click that. Notice that Google Calculator uses the arctan notation, which is fine. And let's see, I want 7 divided by 16. There, so I get 0.4124, and that's the number that I have right there. Okay. How about this composition? So I want to find, again, we're composing trig and inverse trig functions. Now, if this were cosine of cosine inverse of 5/7, I wouldn't even have to think about it. The result would be 5/7. Notice that 5/7 is in the domain of inverse cosine, right? It just has to be between -1 and +1, which it is. All right, but so this is not cosine out here, though. We seem to be composing a trig function with a different inverse trig function. So how do I go about this? Well, I'm going to let theta be the thing inside, the sort of inside evaluation, the cosine inverse of 5/7, because we've seen by now that what this expression means is we can think of it anyway as an angle whose cosine is 5/7. So using an angle letter like theta is a good idea because it gets us kind of thinking in the right way. Okay, so I have an angle whose cosine of 5 is 5/7, and I want to take the sine of that angle. The easiest thing to do here, I think, is to draw a picture at this point, right? Theta is an angle whose cosine is 5/7. So draw an angle like this one, whose cosine is 5/7. Now cosine, remember, is adjacent over hypotenuse. So I'm going to take my angle, put it in a right triangle like this, make the adjacent side 5 and the hypotenuse side 7. Okay, now I have a picture of theta, and what do I want to do? I want to find the sine of theta. Well, sine is opposite over hypotenuse, so that would be this side, this vertical side divided by the hypotenuse. I don't know what the vertical side is, but I can figure it out using the Pythagorean theorem, right? So that's the first thing I'm going to do here, right? Call the opposite side x. Then by the Pythagorean theorem, 5 squared plus x squared equals 7 squared. And I can solve that equation for x pretty easily. I'll just do a little bit of algebra there. And I wind up with, so let's go a little bit more slowly here. Right, so this means what? 25 plus x squared equals 49. And then when I subtract 25 from both sides, that means that x squared is equal to 49 minus 25 is 24. And then I take the square root of both sides, and technically I would get plus or minus square root of 24, but x is the length of a side of a triangle, so it can't be negative, and I'll just throw out the negative solution, and I get x is the square root of 24, or about 4.899 on my calculator. Okay, remember what we wanted to do was to find the sine of this angle, so that's going to be, again, opposite side, that's what we just found, the 4.899, divided by hypotenuse 7, and so that's our result. Right, so the sine of this thing, this is what we started with. Well, that's just the sine of theta because we introduced the variable theta to stand for that thing inside. And I just do opposite over hypotenuse, and on my calculator, that comes out to be about 0.7. Okay, a similar example. Again, here I'm composing a trig function with an inverse trig function, but they don't sort of match, right? So if this were tangent of tan inverse of 6x, then I would just have 6x as my result, right? Because those inverse functions undo one another. But these aren't inverse functions, so I have to be a little bit more careful. Again, I'm going to introduce a variable theta for the inside quantity, the tan inverse of 6x. Because the tan inverse of 6x I can think of as an angle whose tangent is 6x. And the next thing I will do, very similar to the previous example, is I'll draw a triangle with this angle in it, right? So I draw a right triangle and I put the angle theta in it, right? So much like I did above. This time, theta is an angle whose tangent is 6x. Well, tangent's opposite over adjacent. So that means the opposite divided by the adjacent has to give me 6x. There's actually lots of different ways to do that, but probably the easiest is to make the opposite side just 6x and the adjacent side 1. And now it works, right? Opposite over adjacent is 6x divided by 1, which is just 6x. Okay, so now I can see theta, and I want to find the sine of theta. Well, sine is, again, opposite over hypotenuse. So I'm going to need to figure out the hypotenuse, but I can do that using the Pythagorean theorem. So if we let h be the hypotenuse, then that means square of the hypotenuse is equal to 1 squared plus 6x squared, right? The sum of the squares of the other two sides. Now be careful, I mean, 1 squared is just 1, that's not that hard, but when you square something like this, you have to square both factors, both the 6 and the x. So 6x all squared is 36x squared. Then again, this is equal to h squared, so I'm going to take the square root on both sides to figure out what h is. And I disregard the negative square root, right? Because again, h is a sine length, so it's not going to be negative. Okay, so here's my formula for h. I want to find the sine of theta, which is opposite 6x over hypotenuse, which is the h we just found. So now I just have to write those things down. Right, so this is where we started. That's equal to the sine of theta because we introduced the variable theta for the inside quantity, and that is opposite over hypotenuse. And you can see that we've expressed this thing in such a way here where there's no trig functions involved in the expression, which is what we wanted to do. Okay, that's good for a quick introduction to inverse trig functions. Do read section 6.3 and try the practice problems at the end of that section, and take good care of yourselves, folks.